Hello, everyone. In the previous class, we have discussed approximate solution of the Poisson-Boltzmann equation, and I promised you that there is also an exact analytical solution of this equation, and we will discuss analytical solution in this lecture. Having derived an analytical formula for the potential that depends on the coordinate, that is potential as a function of distance from the surface of the semiconductor, I will present some calculation results which show the field effect in the semiconductor, that is the ability to control the concentration of charge carriers of both types, electrons and holes, by applying an external electric field or equivalently by changing the surface potential. All right, so I would like to start with an interesting analogy between Poisson-Boltzmann's equation and Newton's second law. Let us assume for definiteness that the semiconductor is of p-type and only acceptor impurities are present. The treatment that I will present is easily extendable also to the case when the semiconductor contains both donors and acceptors, but to keep the formulas a little bit shorter, I assume that only acceptors are present. Poisson-Boltzmann's equation tells us that the second derivative of the potential on the surface of the semiconductor, that is when x equals 0, is maintained at the value phi s, phi surface, whereas far away from the surface at large values of x, the potential goes to 0, and also the electric field goes to 0 at large distances from the surface. And our main task is to figure out how the potential depends on the coordinate x, that is on the distance from the surface inside the semiconductor. Poisson's equation tells us that the second derivative of the potential is negative volume charge density divided by the electric constant. So d2 phi by dx squared is negative rho of x over epsilon naught epsilon, where epsilon naught is the vacuum permittivity, 8.854 10 to the negative 14th farad per centimeter, or 10 to the negative 12 farad per meter. And epsilon is the relative dielectric constant of the material, or relative permittivity, which in semiconductors has a typical value of around 10. Right. Now the charge density is due to, in a p-type semiconductor, it is due to electrons, holes, and negatively charged acceptor impurities. So the second derivative of the potential with respect to coordinate is negative. Charge density is the elementary charge times the concentration of all positive charges minus the concentration of all negative charges. So our concentration of positive charges. The first term gives me the whole concentration at a point x. Okay. Na, acceptor concentration, is to a very good accuracy whole concentration far away from the surface. That is, I assume that the doping level greatly exceeds the intrinsic carrier density. So I can approximate the bulk value of whole concentration with acceptor concentration. And this is far away from the surface. That whole concentration has the bulk value of acceptor concentration, but closer to the surface, the potential starts to play a role. So this needs to be multiplied with Boltzmann's factor e to the power negative local value of the potential, phi of x, divided by the thermal voltage V thermal, which is the ratio of thermal energy kT to elementary charge. Now, of course, this formula, the negative sign in the exponential reflects the fact that holes are positively charged particles, so they tend to avoid regions where the potential is positive, and they tend to be attracted to the regions where the potential phi of x is negative. Now, next, we have minus Na, this is just the concentration of negatively charged acceptor ions, okay, assumed to be uniform, independent of X. And finally, we have negatively charged electrons, electron concentration now, so negatively charged, hence the minus sign here. N intrinsic squared over N acceptors is the bulk concentration of electrons. This is multiplied due to mass action law. This is multiplied with exponential to the power 5 of x potential divided by the thermal voltage. Again, electrons are negatively charged particles. They are attracted to the regions where the potential is positive, repelled by the regions where the potential is negative, so hence the plus sign in the exponential right here. So this would be our charge density, and it is divided by the dielectric constant epsilon naught epsilon of the semiconductor. Now let us write the right-hand side of this equation, of the Poisson-Boltzmann equation, as negative derivative of some function u that depends on the local value of the potential phi, and it is the derivative du by d phi, where the function u is defined by this formula, and as you see, if you differentiate this expression u of phi with respect to its argument phi, you will indeed get the right-hand side of the Poisson-Boltzmann equation. And now notice that, so we have d2 phi by dx squared is negative du by d phi. This expression, this second order differential equation, bears striking similarity to Newton's second law that describes one-dimensional motion of a massive particle with mass m in the presence of the potential u of x, where x is the coordinate of the particle. So mass times acceleration, the second time derivative of the coordinate equals force, which is the negative gradient, negative derivative of the potential with respect to coordinate. So just compare these two. The difference between the two equations is purely notational. So what is called time in Newton's second law, t, is the coordinate x in the Poisson-Boltzmann's equation. So t in Newton corresponds to x in Poisson equation. The coordinate x in Newton's second law, the coordinate of our particle, corresponds to the potential, to the local value of the potential phi. The mass in Poisson's equation is just 1, yeah, because nothing multiplies the second derivative of phi with respect to x in Poisson-Boltzmann's equation. All right, so this is the analogy, and now we can make a powerful statement. In a mechanical system, energy is conserved, unless you have things like dissipation or external drive and external force acting on the system, which depends on time. But if nothing like that is present, then the total energy of our particle will be conserved. And the total energy is the sum of kinetic energy plus potential energy. Kinetic energy is mass velocity squared divided by 2. So this is mass velocity squared over 2, plus the potential energy u of x. It's the energy, and it must be constant independent of time. So we can draw the same conclusion with respect to Poisson-Boltzmann's equation. Kinetic energy, 1/2, mass is 1. 1/2 velocity-like term would be d phi by dx. Now it needs to be squared in order to get kinetic energy. Potential energy is u of phi. It is written down here, and it must be a constant. All right. Now, if thinking by analogy is not something that you particularly like, if this type of reasoning seems a little bit suspicious to you, here is the rigorous derivation of this conservation law. So let's start with Poisson-Boltzmann's equation again. The second derivative of the potential with respect to coordinate x is negative du by d phi, where the potential u is defined by this formula. Okay. And multiply both sides of this expression, of this equation, by the derivative d phi by dx. Using this identity, so if I multiply the second derivative, d2 phi by dx squared, with d phi by dx, and this is the same as taking the derivative of d phi by dx all squared with respect to x, and multiplying the result by 1/2. Indeed, by using the chain rule, d by dx of d phi by dx squared is 2. d phi by dx, I have differentiated the square of a function. Now I need to differentiate the function itself, giving me d2 phi by dx squared. So I need to compensate for this factor of 2, which pops out after differentiating the square with respect to x. So that's why I multiply by 1/2. In the right-hand side, I have du by d phi times d phi by dx, which is the same as du by dx. But u is a function of, where u is a function of phi, which in turn is a function of x. So again, using chain rule, du, which depends on phi, which depends on x, by dx is du by d phi times d phi by dx, chain rule. So what do we get? This thing equals negative this thing, or this thing plus this thing must be 0. Right? Of course, when you take the sum of derivatives of two functions, is the derivative of the sum of these two functions. So let us call the sum 1/2 d phi by dx squared plus u. Let us call it e. And the derivative of this function e, it is like energy-like function. It is not energy in the mechanical sense, in the same sense as in classical mechanics, but it plays the role of energy. So this energy-like function is 1/2 d2 phi by d phi by dx squared plus u of phi, and it must be conserved. Kinetic energy is 1/2 square of the first derivative of the potential, and potential energy, like I said before, it is written in this is the potential energy. I would like to write, to draw your attention to the fact that the last term in the brackets can be written down as exponential to the power phi minus phi threshold, phi t, divided by the thermal voltage. So I have, where the threshold potential is given by this formula. Phi t is given by this formula. Twice the thermal voltage times natural logarithm of the ratio of acceptor concentration to the intrinsic concentration. And it is at the threshold potential. The physical meaning of the threshold potential is that when the surface potential has this value phi t, the threshold value, then the concentration of minority electrons at the surface at x equals 0 will become equal to the concentration of majority holes far away from the surface and the bulk of the material. So if the surface potential is below the threshold potential, then you are still in the depletion regime. Okay, but when you reach the threshold potential, conductivity inversion happens near the surface, and the minority electrons near the surface becomes actually majority carriers near the surface. But in the bulk, the majority carriers are still holes. All right. So I hope I have. So this was the rigorous derivation of the energy-like quantity which is conserved. Now, what can we do with this energy-like quantity? Well, this is our energy-like function. We can establish its value using boundary conditions. The boundary conditions tell us that far away from the surface, that is, when x goes to infinity, and by infinity, I do not mean like infinity in the sense of the other end of the universe. I mean infinity may be sufficiently far from the surface for the electric potential to drop to zero, and for the electric field to go to zero. And this happens, I mean, depending on the doping level, this may happen, let's say, at the distance of 10 micrometers, or maybe 100 micrometers, if you want to be on the safe side. So infinity is really not mathematical infinity, but physical infinity. All right, so applying these boundary conditions at x goes to infinity, setting the value of the potential to zero, setting the value of the electric field, negative d phi by dx is the electric field, to zero, we find that this energy-like function is this value of the potential energy-like function at x goes to infinity. So I really should have replaced, so this infinity means x goes to infinity, not phi goes to infinity. Phi goes to zero at x goes to infinity. So substitution of phi equals zero in this potential energy-like function gives us this value of the energy. So let's return to the potential energy-like function written here, or maybe here. When phi goes to infinity, you get, okay, negative E n acceptor over epsilon naught epsilon. Negative E n acceptor over epsilon naught epsilon. The first term becomes phi thermal, V thermal, thermal voltage. Exponential goes to zero. The second term goes to zero. The third term becomes n intrinsic squared over n acceptor squared times V thermal. So V thermal times 1 plus n intrinsic squared over n acceptor squared. And this is indeed what we get. All right, so this is our energy-like, the actual value of the energy-like function at infinity. Now, so we have this E, the value of E, and we know that it is a constant independent on the position and on the position and on the potential phi and on the position x. We can solve this equation for d phi by dx. The solution is quite simple. D phi by dx is square root. So subtract u of phi from both sides, multiply by 2, take the square root. D phi by dx is square root of 2 times energy E, which is constant. It only depends on the level of doping and on the temperature, on the intrinsic concentration. So square root of 2 times E minus u of phi. But now we need to be careful. Square root of a number is by definition a positive number. So square root of 4 is 2 by definition. But we shouldn't miss the negative 2, right? So we shouldn't miss the possibility that there can be a minus sign. When do we have the minus sign in the expression for d phi by dx? Well, if the surface potential phi surface is positive, then the potential should be decreasing with the coordinate x as you move away from the surface, if the surface potential is positive. Hence the sign, if the surface potential is positive, then the sign of the derivative d phi by dx must be negative. The potential is decreasing, d phi by dx must be negative. On the other hand, if the surface potential is negative, then the potential phi of x must be increasing from the initial negative value to the value 0. So if the surface potential is negative, then d phi by dx must be positive. Hence, I have to multiply the square root with the negative sign of the surface potential. Sign of the surface potential assumes the value either +1 or -1, depending on whether the surface potential is positive or negative. Sign of x is +1 is if x is positive, and -1 if x is negative. All right, so we have our dphi by dx. Can I solve this differential equation for phi in terms of x? The answer is no, I cannot. But I can consider dx by dphi. I can invert the derivative, dx by dphi, which will be negative sine of phi of x divided by square root of 2 times c minus u of phi. And then I can solve for x in terms of phi. Now, this is, of course, not the solution that people are used to, but it is a perfectly acceptable mathematical solution. It tells you at what position a particular value of the potential phi is realized. So let's say the surface potential is 1 volt. Using this formula, integrating this dx by dphi with respect to phi, starting from the surface value phi surface, yeah, I get this x. So let's say the surface potential is 1 volt, and this formula allows me to determine quickly at what value of x the potential reaches the value of, let's say, 0.9 volts or 0.8 volts or 0.1 volts. Okay. So from the computational perspective, this solution is just as useful as the direct solution given me the function phi of x. So this is an inverted solution, so to speak. I get the argument in terms of the function value, not the function value in terms of the argument. All right, so now I wrote a little code that implements this solution by performing the integration. I assumed like a hypothetical semiconductor with no, it's not hypothetical semiconductor. It is silicon. Sorry, I took silicon with the intrinsic concentration 10 to the 10th. I assumed the doping level, acceptor doping level of 10 to the 16th. This gives me the threshold potential twice v thermal n natural logarithm of n acceptor over n intrinsic, so natural logarithm of 10 to the 6. 6 times 2.3, whatever the value is. So the threshold potential turns out to be 0.69 volts. And if the surface potential is 1/10 of this value, then this is how the potential decreases with the distance, with the coordinate x. It decreases somewhat similar to what you would expect from the Debye formula, or similar to what you expect. This graph looks more like a parabola. So this is well described by the depletion approximation. The second curve shows the charge density. Charge density due to ionized acceptors, negative ions, and also due to electrons and holes. In the depletion regime, which is realized for this value of the surface potential, the charge density is near the surface is mostly due to the ionized acceptors, and indeed, like the numerical value of the charge density at the surface is negative 1.5 millicoulombs per cubic centimeter, whereas the charge density due to ionized acceptors is negative 1.6 millicoulombs per cubic centimeter. Okay, and here is the mistake. This division sign is unnecessary. So coulombs, either coulombs per cubic per centimeter cubed, or coulombs multiplied with centimeters to the negative 3. But I am not going to record this video again. I'm just drawing your attention that there is a small typo here. All right, so okay, so far so good. nothing unexpected. Now, what happens if we increase the surface potential? This is the value 0.8, the threshold potential. Then the depletion layer, in this case, the depletion layer develops in its full glory. The value of in this depletion layer, the charge density due to ionized acceptors and also holes and electrons in the depletion layer. It has the value very close to negative 1.6 millicoulombs per cubic centimeter. Then we have this transition region where the depletion layer ends. So the width of the depletion layer is somewhere here, somewhere in the middle, 0.25, I would say, or maybe a little bit more, 0.27. And the standard theory of the depletion region predicts the value given by this formula discussed in the previous lecture, 0.27 micrometers. Yes, so that's correct. Concentration of holes near the surface for this value of the surface potential is very small, 4.85, 10 to the 6th inverse cubic centimeters, which is 10 orders of, no, maybe 9 orders of magnitude, whatever, smaller than the acceptor concentration. Concentration of electrons near the surface will be given by the mass action law, n intrinsic squared divided by the hole concentration near the surface. So n intrinsic squared is 10 to the power 20, divided by 5, 10 to the 6. So it is 0.2, 10 to the 14th. 0.2 10 to the 14th is still 2 orders of magnitude smaller than the acceptor concentration. So that more than 100 times bigger than smaller than the acceptor concentration. So yes, the depletion approximation in this region indeed holds quite well. Now what happens when the surface potential reaches the threshold value? In this case, we see that the surface charge density at x equals 0 has this large, relatively large negative excursion, negative peak. So at the surface charge density is primarily due to electrons. It is now, when the surface potential has the threshold value, then the concentration of electrons at the surface, x equals 0, is equal to acceptor concentration. And so the total surface charge density is negative elementary charge times acceptor concentration times 2. And this factor of 2 comes due to the fact that we have ionized acceptors, and also we have electrons whose concentration at the surface is exactly the same as acceptor concentration at threshold surface potential. And of course, hole concentration at the surface is negligibly small, mass action law. Finally, what happens if your surface potential is twice as big as the threshold potential? So I have increased the surface potential by another 0.7 volts, twice as much as the threshold potential. The depletion layer does not grow anymore. The depletion layer doesn't care. So notice that here the depletion region width is 0.3 micrometers when the surface potential has the threshold value. And when it has twice the threshold value, the depletion region width still has the value of 0.3 micrometers, right? But the inversion layer, the electron-rich inversion layer, becomes bigger in size, a little bit wider, right? And of course, the concentration of electrons in the inversion layer grows exponentially strongly with the surface potential. So I do not the electric charge density goes down to very large negative values, which I didn't include in this graph, because otherwise you wouldn't be able to see this part of the graph, which is visible. All right, so I have explained the field effect, I have explained the inversion, conductivity inversion effect, and the final remark that I would like to make is that recently, something like a year ago, I have stumbled upon this very interesting paper. So you would think that this Poisson-Boltzmann's equation, come on, it's old. It has been introduced long ago. Maybe 60 years ago, maybe 50 years ago, long ago. So everything that could be said and found in relation to Poisson-Boltzmann's equation must have been discovered long ago. And yet, so this cool guy, Pedro Pereira from Mexico, he was able to find a nice asymptotic solution of Poisson-Boltzmann's equation, which gives you not the coordinate x as a function of the potential, but the potential as a function of the coordinate x, and this solution covers exactly this region near the inversion, where the inversion happens. So exactly this region of small values of x, when the surface potential exceeds the threshold value. So I find this pretty cool. All right. So thank you all very much for your attention, and I'll see you. We are done with the topic of charge carrier concentration in the presence of non-uniform electric potential, and our next topic will be generation recombination processes. So see you in the next class. Goodbye.